So let's move to the last speaker for this session. That is Luca Cacciapuoti. That he will talk about the ALMA multi-band multi-scale dust study of LL1527, evidence for some millimeter dust grains in the envelope of a Class I YSO.
Oh, sorry, that was awfully long title. Hi, everyone. I'm Luca. Let me reduce these, otherwise, okay. I'm a second year PhD student at YSO. I'm working with Leonardo Testi, who's actually based in Bologna, and a bunch of other collaborators, of which you see a few listed there. And what you see here is a JWST near-cam image of the object that I'm studying, L1527, on top of which I overplotted the ALMA band 3 data, which is just part of the data we used for this project. Okay, so as many other people have shown during the week, this is what we think is a kind of a standard model for planet formation. So you usually start from a pre-stellar core, this thing collapses and you form a protostar at the center, and then due to conservation of angular momentum, you form a disk that is a kind of early disk in the class, what we call class 0-1 stage. So the first 10 to the 5 few 10 to the 5 years in planet formation, and then in this phase you still have a collapsing envelope, as you see in the left, the protostar at the center, the disk, and then also outflows and jets. And then as time goes by and the envelope collapses onto the disk and the star gets more and more evolved, you basically are left with a disk of dust and gas. You disperse the envelope, the outflows are not there anymore, and now you're left with this isolated disk in which planets can grow. And this lasts for a few million years until you're left with your planetary system that can just live as long as your star. And the phase I am focusing on is the class 0-1 phase, so the very early stage of planet formation. Now, why I am studying early dust around these early objects? There's a few reasons. One of the first reasons is that in the last few years, we realized that planet formation, while we thought it was happening in this isolated disk where you start to grow dust and gas together to make your Jupiters or your inner terrestrial planets, we're actually realizing that maybe planet formation in terms of aggregation of dust to make your planetary cores is starting earlier. And you see here a plot from Tikhonets et al. In 2020, in which they show a comparison between the mass in the exoplanets we know, or at least we knew at the time, and they compared it to the mass of dust in the disks around the young class 0 and class 1 objects and class 2 disks. And you see that the dust mass that we see in class 0 and class 1 disks is enough to explain the exoplanets that we know, while in class 2, that's not the case anymore. And so this is a hint to the fact that the dust grains in the class 0 and class 1 sources have already grown up to be large boulders or even planetesimals, right? So planetary cores, or at least the building blocks of those, of which ALMA, VLA, and other interferometers are blind to, because they're just too large boulders, so you don't really observe them that way. And so definitely studying when dust starts to grow and agglomerate kind of set the onset of planet formation. So we want to go as back in time as we can, and that's why I'm focusing on early objects. Then the second reason is that since these objects have, as I said, collapsing envelopes, it's also important to realize what kind of grains you have in these envelopes, because the amount of large or small grains you have, since these are coupled in different ways through electric charge to the magnetic fields that you have in the environment, then can cause angular momentum to be transported in different ways. And then basically the fact that you have either small or large grains can cause you to have small or large protoplanetary disks, which, as you can imagine, then it's really important for the final exoplanetary system that you're going to form, right? And then finally, we do have some previous hints of dust growth in the envelopes of some of these objects. So this is a study by Galametz et al. In 2019, in which they used the Calypso sample to study the dust grains, the dust properties in the envelopes of a bunch of sources. And basically what you can get from this plot is that basically the objects that have beta, this beta on the y-axis below 1, can be interpreted as having large, when I say large, I mean millimeter grains in their envelopes. And so basically we want to start from here and kind of advance what they started using more frequencies, more scales to trace eventually gradients and so forth. So how do we study dust in the first place in the interstellar medium or in these kind of environments? Is we look for this beta parameter that I just said. Beta is basically the exponent of your opacity. So if the opacity of dust is a power law of the frequency, beta its exponent. And if we want to study beta because beta itself is linked to the dust grain properties, as you see in this plot from Test et al. In 2014. And in particular, given a certain geometry and a certain porousness of your grain, then usually a beta of about 1.6, 1.7 is typical of interstellar medium dust grains, while betas below 1 imply a certain amount of growth. In fact, here you see that on the x-axis, you have the maximum grain size. And when your beta goes below 1, then you start having grains of a millimeter or even a few centimeters. So we want to get beta to get something on the grain sizes especially. And if you read this beautiful review by Antonella Natta in 2007, she tells you that if the emission is optically thin, if the emission of your source is optically thin, and if you are in the Rayleigh-Jeans approximation, then beta is alpha minus 2, where alpha is the spectral slope of your, well, the SCD of your object. So basically, just as an example, if you look at a disk and you plot its SCD, you will have the contribution of the star excess in the infrared that is given from the dust. And in particular, in the millimeter regime, you will see that the flux is usually well approximated by a power law, and the exponent of this I call alpha. So what Antonella et al. Were saying is that if your emission is optically thin and you are in Rayleigh-Jeans approximation, then if you can measure that alpha, so if you can have a robust measure of the SCD of your object, then you can get beta just simply doing alpha minus 2. And beta again is linked to the grain sizes. So the object we study is L1527 in Taurus, is an object that is very close. It's very bright. And for this reason, you have a lot of, and also it's young, which protostars, I mean, they are kind of rare objects because of the timescales involved. So you have a lot of archival data with ALMA. And actually, for the first year of my PhD, I've been basically reducing, self-calibrating all of the data that you can possibly get for this source in the archive, except I've been flagging all the lines because I'm working with the continuum. And so basically, we put together ALMA, both the 12-meter and the 7-meter arrays in order to then work in the visibility plane, as you see on the right. So just for reference, the contours there is a quick image that I made of the band 3 data. And what I'm highlighting there is that in the middle, you have something that is a protoplanetary disk that is more or less in the green shaded area, while the farther out you go, the more the emission will just be given by the envelope in the image plane. The point is that we decided to work in the UV plane to stay rid of these kind of non-linearity effects that you can introduce, artifacts that you can introduce, cleaning the visibilities. But the point there is that in the UV plane, at each baseline, you still see the emission of everything, right? Both the disk and the envelope. And so we try to model these two. And we want to model the visibilities just because we want to focus on the SCD of the envelope to study dust grains in the envelope of this object. And so we need to subtract the emission of the disk. So basically you see that we fitted the visibilities with a Gaussian, which is usually a good approximation of your blobby disk. And then we also kind of self-consistently added a power law to that to kind of model this spherical envelope. And then once we have the Gaussian model, so the green model, we can subtract that from the data to kind of have left just the envelope fluxes. And so we did this also for ALMA band 4, band 6, and band 7. So we're really trying to go multi-scale and multi-frequency. So once we have the model, we subtract, as I was saying, the disk. And so here what you see is in the big plot, you see different colors are different bands. And here we have already subtracted the disk. So the amplitude level that you see on the left is basically the flux of the envelope only emission. And then on the right side of this plot, I have alpha, so the spectral index. And the spectral index we have computed for each UV distance bin, as you see, for example, in the inset that I put there. And that more or less can be traced in a physical radial scale. So we're really trying to measure the alpha, the spectral index, across scales in the envelope of this object. And as I said before, now that we have alpha, we can get beta just by doing alpha minus 2, right? But the problem is that actually, as I said, you need to be optically thin and in the RJ approximation in order to say that beta is alpha minus 2. So we checked that we are in the optically thin regime. So on the left here, you see that basically what I'm doing here, I'm comparing the emission of the envelope. So once the disk has been subtracted in orange to basically a black body of a given dust temperature that is typical, kind of given by a typical profile of protostellar envelopes. And then basically by the ratio of the two, you can get the optical depth. And you see that basically any scale, the optical depth is well below 1, especially already at 100 or 200 AUs, where you are really like just probing the envelope scales. And the problem here is that if you use the same profile that I use for this black body here, and you kind of make your model and you post-process it with the radiative transfer, right? So you have a disk, an envelope, and then to this envelope, you can get this temperature profile just by doing radiative transfer. And the point is that this temperature drops very quickly in the envelope, and you are at about 20 Kelvin at already 200 or 300 AU, as you can see in this plot on the right from Flores Rivera et al. And so the point is, when you go to these low temperatures at the millimeter wavelengths that we probe, then you are out of the Rayleigh-Jeans regime. And so it's not true anymore that beta is just alpha minus 2. So we correct for that. And basically what this plot here shows is the alpha minus 2 approximation is in black. And then what we, once we correct once we correct for the temperature, then we get a beta that, as you can see, is very close to alpha minus 2 when you are in the inner scales, and so the temperature is high. But the outer and outer you go in the envelope, the lower the temperature gets, and so the more important the correction gets itself. And then basically we just fit a line, the orange line, to the beta points in order to get kind of the gradient in the envelope. So basically what this is showing you is that you have a gradient of beta in the envelope of L1527, and beta traces the optical properties of dust. So somehow dust is stratified in the envelope. And importantly, if you compare to the plot that I showed at the beginning, you see that you have in the outer scales a beta of about 1.6, while if you go in, you have beta even below 1, which is usually a sign of growth. So the ideas why this is happening, at least the ones we have, is that either we have a differential collapse. So when we started from a pre-stellar core, you already had different kind of grains, and then these started to collapse differently because they're differently coupled to the gas. And so you have the bigger grains in the lower parts of the envelope and the smallest ones upwards. This is a possibility, but we really don't think it's our favorite, just because L1527 is kind of, it's young, but it's also evolved among the youngest. So we think that the largest grains would have already fallen, so just by timescales on the disk, and so we wouldn't be able to observe them in the envelope. The other thing is that the grains might be growing in situ in the envelope. The problem here is that all these simulations, of which the papers I referenced there, they show you that you can't really grow grains in the envelopes up to, well, more than about 5 microns. And here we find evidence for like millimeter grains. So there is something that we really need to take into account when interpreting beta or running our simulations that needs to be changed. Because there is basically a 2 orders magnitude difference. And then the third hypothesis is that there is a transport, which means you actually grow your large grains in the disk, where you have densities and lifetimes of the disk are long enough and high enough to build large grains, and then outflows and jets entrain these grains and shoot them back in the envelope. And in another work, what we are trying to do is to kind of check if these, so this scenario that was shown by simulations in Tsukamoto et al. In 2021, we are trying to see if we can observationally test it to kind of see if these protostars are acting like chimney flues, right? You have the ash in the disk and then you shoot it back upwards. And so we are looking for correlations between the beta, so somehow the grain size, and the mass loss rate of jets and outflows of these objects. And we have some preliminary results now. We're also working on the outflows, but with the jets, we see that the stronger you have in terms of jets, so the stronger the jets are, the lower is the beta in the envelope, so the larger are the grains. So it seems that when you have strong jets, you shoot in the envelope larger and larger grains. And so the conclusions are that we really need while there was a sample study by Galamez et al. That I showed in the beginning, we really need to use multi-bands with ALMA, especially because ALMA has a higher sensitivity. The errors are way lower, your both calibration and statistical errors. Using multi-bands and multi-scale approach allows you to robustly constrain also gradients along the envelope. And then finally, what we found is a stratification of properties in these particular objects, and we discuss the possible reasons for that. One of which is transport due to jets and outflows. And with this, I thank you for your attention.
Thank you very much, Luca. So, are there any questions for Luca? Yes, Claudia.
Hi, Luca. Thanks a lot. Very, very nice talk and very nice results. So I have a curiosity. I see from the plot you're showing here, the InPrep work, that you try to see which one of the three mechanisms is the most relevant. What if more than one are at play? Do you see so are there any strong signature that you can discriminate, or if more than one are at play, we are basically blind?
Yeah. So as I said, the differential, thanks for the question. As I said, the differential collapse is, we put it in the discussion because as usual things can happen, but just based on lifetimes, we think it's probably not the case, at least specifically for L1527, might be the case for other sources. I think that the way to discriminate whether there is an interplay of early growth and transport, or just one of the two, really come from simulations in the next years. Because up to now, the papers that I've cited before, so Le Bruyère 2023, Silsby 2022, some of these are just even analytical, actually. They show you that it's like at the densities of these envelopes, which is about 10 to the 7, 8 particles centimeter cube, and like at lifetimes of these objects, you can't really grow anything that is bigger than a few microns, like 2, 5 microns if you really push things. And if you find millimeter, then you have a factor, like 2 orders of magnitude problem. The problem is there that these simulations, they kind of all rely on dust coagulation and fragmentation models that go way back in time, and they are perfectly fine. It's just that sometimes we have disregarded some effects like dust back reaction on the gas, or for example, the interaction with the magnetic field that maybe can keep your grains lifted in the envelope just by charge. So I think definitely with the simulations, I know there's people working on it. I know Ugo Le Bruyère is working with it, especially on the magnetic fields part. And I think with the simulations, people will really tell us if in fact it's impossible to grow these grains, and then we definitely need a way to push them back. And I think transport looks like a promising way.
Thank you.
Thank you, Luca. Are there other questions for Luca? If not, okay, Joshua.
Hi, so amazing talk. Thank you very much. I really like your methodology, but I had a more general question because it's not my topic. So if you want to go for a multi-band, multi-scale approach and you want to set up your observation for proposal, would it be best to choose configurations which match the UV coverage so you have a fair comparison, or do you change configuration to fill in your UV coverage to go for more scales? So I think first, as you said, it's a lot of data that we need, right? If we want to do this, like here we really squeezed the archive and we put like ACA and ALMA 12-meter array together in a bunch of scales and so forth. So we do have a proposal on this actually that was accepted. I'm not the PI, the PI is Łukasz Tikoniec. And what we did was really, once again, just to really optimize what we have in the archive, we really went there and checked which bands, which wavelengths we have and if you had 7-meter or 12-meter array, and we just kind of decided to, since we really need a statistical view on this, we just decided to take all the objects for which you have at least a few wavelengths or a few scales and complement that. We didn't really
it's not a big problem at this, also because it's large scale structure. So it's not really a problem if you have the perfect UV coverage to have circular beam or something like that. So we really tried to get the most from the archive and complement that regardless of the fine details, fine tuning of things, right? So yeah.
Thank you, Luca.
Thanks.
Okay, if there are no other questions, this session ends